Hello and welcome to this presentation of the STM32H5 Analog-to-Digital Converter, or ADC, and Digital-to-Analog Converter, or DAC. It will cover the main features of ADC1 and ADC2, which are used to convert analog voltages, like sensor outputs, to digital values for further processing in the digital domain. The DAC is used to convert digital signals to analog voltages, which can interface with the external world and also with on-chip peripherals such as comparator and operational amplifier. Let's start with a description of the features of the ADCs. Up to two 12-bit analog-to-digital converters are integrated inside STM32H5 products. The input channel is connected to up to 20 channels capable of converting signals in either single-end or differential mode. Several functional modes are supported. They will be described in the next slides. The ADCs can convert signals at a rate of 5 megasamples per second in 12-bit mode on fast channels in the STM32H56X and STM32H573. The maximum performance for STM32H503 is 2.5 megasamples per second. All the packages support fast channels, which are ADC inputs 0 to 5. Those channels are designed to have a low resistive analog switch on the signal path. There are also several different triggering methods. The injected group can preempt the execution of the regular group sampling sequence. In order to offload the CPU, the ADC has an analog watchdog for monitoring thresholds. The ADC also offers oversampling to extend the number of bits presented in the final conversion value. The maximum oversampling ratio is 256. ADC's conversions are organized in two groups, regular and injected group. Raw samples acquired by ADC may be processed by the oversampler and offset compensation units before being provided to the software. For power-sensitive applications, the ADC offers several low-power features. This slide shows the general block diagram of the ADC. The main important subunits of the ADC are the power supplies and on-off control, the analog front end, the trigger logic, the digital backend including the analog watchdogs and the AHB slave interface, the clocking. The next slides detail all these subunits. The ADC has two clock inputs, ADC CK and ADC HCLK. The AHB interface belongs to the ADC HCLK clock domain. Regarding the digital part of the SAR ADC, there are two options. By using ADC CK, there is no limitation of the CPU nor bus clock speed. By using ADC HCLK as the reference clock, it's possible to have fixed trigger latency from the timer trigger to the start of ADC conversion. ADCs have the following analog input channels: up to 20 external channels, 4 internal dedicated channels, 1 channel for internal reference voltage, VREF-INT, 1 for internal temperature sensor, vSense, 1 for VBAT monitoring channel, VBAT divide by 4, and 1 for the internal digital core voltage, VDD core. The analog switch inside the I/O has a resistance which increases when the analog switch supply decreases. For the cases where VDD-A and VDD are low, there's a possibility to enable a voltage booster which will supply the analog switch and guarantee low resistance. It is recommended to use the VDD-A supply for the analog. But when VDD-A is lower than 2.7 volts and VDD is larger than 2.7 volts, the power supply can be switched to VDD. If both VDD-A and VDD are lower than 2.7 volts, the voltage booster should be enabled. This slide describes the sampling time control of ADC. The first step of a conversion consists in loading the sample and hold capacitor with the voltage to be measured. Longer sample times ensure that signals having a higher impedance are correctly converted. The sampling times in ADC clock cycles are listed on this slide from 2.5 to 640.5. The sampling time can be programmed individually for each input channel of ADC. The ADC implements two other mechanisms to control the sampling time. The first one is the bulb mode, which works only in discontinuous mode. In this mode, sampling starts immediately after the last conversion finished without going to idle state. This provides less latency from the trigger signal to the start of the conversion. The very first ADC conversion after the ADC is enabled is performed with the sampling time programmed in SMP bits. The bulb mode is effective after the second conversion. The second mechanism is the sampling mode based on the trigger signal. Rising edge starts sampling, falling edge stops sampling and starts the conversion. ADC provides an automatic offset calibration procedure that controls the whole calibration sequence, including the ADC power on and off. As the offset can be dependent on the voltage or temperature, it might be necessary to recalibrate in case of significant reference voltage or temperature change. Each ADC has 3 integrated analog watchdogs with high and low threshold settings. The ADC conversion value is compared to this window threshold. If the result exceeds the threshold, an interrupt or timer trigger signal can be asserted without CPU intervention. Regarding ADC1, the analog watchdog 1 also has a filtering capability. If data is out of range for a number of times higher than the value specified in AWD field in ADC-X HTR1 register, the AWD-X flag is set and the corresponding interrupt is issued. The STM32H5's ADCs support a deep power down mode. When the ADC is not used, it can be disconnected by a power switch to further reduce the leakage current. Auto-delayed mode makes the ADC wait until the last conversion data is read before starting the next conversion. This avoids unnecessary conversions and thus reduces power consumption. The power consumption is in function of the sampling frequency. For low sampling rates, the current consumption is reduced almost proportionally. All the values in this slide are related to STM32H56X and STM32H573 MCUs. For STM32H503, performance is halved. The ADC supports up to 5 megasamples per second of 12-bit conversion at a frequency of 75 MHz. When associating a master and a slave ADC, the interleaved mode maximum performance is 1 sample every 8 clocks, so 9.3 megasample per second at 75 MHz clock. The ADC includes the oversampling hardware, which accumulates data and then averages them without CPU assistance. The oversampler can accommodate from 2 to 256 times samples and write shift from 1 to 8 binary digits. The sequencer allows the user to convert up to 16 channels in any desired order. Also, each channel can have a different sampling time. The ADC offers an auto-calibration mechanism for the offset. It's advisable to run calibration in the application if the reference voltage changes by more than 10%. The global conversion time is equal to the sampling time plus the conversion time. The ADC needs a minimum of 2.5 clock cycles for the sampling and 12.5 clock cycles for conversion for 12-bit mode. With the 75 MHz ADC clock, it can achieve 5 megasamples per second. For a higher sampling speed, it's possible to reduce the resolution down to 10, 8, or 6 bits. STM32H503 maximum sampling rate is 2.5 megasample per second for 12-bit mode. The ADC supports several conversion modes. Single mode, which converts only one channel, in single shot or continuous mode. Scan mode, which converts a complete set of predefined programmed input channels, in single shot or continuous mode. And discontinuous mode, which converts a short sequence, a subgroup, that is part of the sequence of conversions at each trigger signal. In this figure, this short sequence includes 2 channels. A built-in hardware oversampler allows improving analog performances while offloading the related computational burden from the CPU. It can sample by 2 to 256 times without CPU support. The converted data is accumulated in a register and the output can be processed by the data shifter and the truncator. 12-bit data can be extended to be presented as a 16-bit data register. This functionality can be used as an averaging function or for data rate reduction and signal-to-noise ratio improvement, as well as for basic filtering. The ADC conversion result is stored in a 16-bit data register. The system can use CPU polling, interrupts, or DMA to make use of the samples obtained by the regular conversion. An overrun flag can be generated if data is not read before the next conversion data is ready. For injected channel conversions, 4 dedicated data registers are available, 1 per injected channel. Data cannot be managed by DMA for injected channel conversions. An injected conversion is used to interrupt the regular conversion, then insert up to 4 channel conversions. Once an injected conversion is finished, the regular conversion sequence can be resumed. The injected conversion result is stored in dedicated data registers. Flags and interrupts are available for the end of conversion or end of sequence. The selection of injected channels can be reprogrammed on the fly. Even if a regular or injected conversion is in progress, you can add a different channel to the queue so that the next injected channel can be different from the previous one. Each ADC supports 9 interrupt events: ADC ready, end of conversion, end of sequence, end of injected conversion, end of injected sequence, analog watchdog, end of sampling, data overrun, and overflow of the injected sequence context queue. DMA requests can be generated at each end of conversion when the ADC output data is ready. The ADCs are active in run and sleep modes. In stop mode, the ADCs are not available, but the contents of their registers are kept. In standby mode, the ADCs are powered down and must be reinitialized when returning to a higher power state. There's a deep power down mode in each ADC itself, which reduces leakage by turning off an on-chip power switch. This is the recommended mode whenever an ADC is not used. The following table shows performance parameters for the ADC regarding the STM32H562 and STM32H57X BGA packages. For STM32H503, please refer to the datasheet. All values are preliminary. Performance is package dependent, so please refer to the datasheet or application note for the package and product dependent information. These peripherals may need to be specifically configured for correct use with the ADCs. Please refer to the corresponding peripheral training modules for more information. Several application notes dedicated to analog-to-digital converters are available. To learn more about ADCs, you can visit a wide range of web pages discussing successive approximation analog-to-digital converters. Now let's look at the features of the DAC. The STM32H5 integrates one DAC module with 2 analog outputs. The DAC output can be routed to internal resources, such as a comparator and operational amplifier, without using GPIO. In stop mode, the DAC can support the sample and hold mode using the LSI or LAC clock source for static conversion. To synchronize DAC and ADC, the same clock source can be used for both peripherals. This is done by selecting the DAC CARE-CK clock instead of the DAC HCLK clock in the RCC. This table shows the typical characteristics of the STM32H5's DAC. The STM32H5's DAC can work between 1.8 and 3.6 volts whether the buffer state is on or off. 10-bit monotonicity is guaranteed. By using sample and hold mode, the current consumption can be drastically reduced. The DAC can handle a sampling rate of 1 megasample per second. Several application notes dedicated to analog-to-digital converters are available. To learn more about ADCs, you can visit a wide range of web pages discussing successive approximation analog-to-digital converters. In addition to this presentation, you can refer to the following presentations: Reset and Clock Control, and Power Management.